Hello and welcome to Forming Analysis using ARGUS Measurements, ARGUS Overview. My name is John Psilopoulos and this is part 2. We're now going to go over the process chain sheet metal processing. Many people think that the ARGUS system is an end result FLD pass or fail. This is untrue. The ARGUS can be implemented as early as your tryout process. A panel can be etched, stamped, and measured to find out a complete roadmap of hotspots and gradients to see where the problem areas on the part are. Here's a perfect example of such a scenario. You can see that a hotspot has developed on the transitional part in the corner of this panel. You can see how also it automatically mapped all the points to the FLD diagram, which gives the die makers and the engineers a roadmap of where to go to fix the die. After the die maker was able to fix the die, they were able to etch it again, stamp it, and measure it once again to see if the problem was solved. And you can see out of this result that the problem was solved and the part is now passing. They can now move on with less time spent to try to fix the error. Now we're going to show you the precision analysis of complex stamping. Here's a 3D shape of a test part. Now you're seeing the full field end result of the ARGUS formability system, which is showing you strains, wall thicknesses, residual stress, and forming limits. The detail of a high strain area is now no longer a guessing game. You can now see exactly what's going on with the material and how it's behaving by dropping a section line over it, which is automatically mapped to a graph and giving you percentages, numbers, so that die makers and engineers can know exactly where to go and how much to fix the die by and see exactly how the part is reacting. We'll now show you an example of a forming analysis of an electro-zinc coated inner tailgate. We've pulled out the corner of this tailgate to show you this example. You can see that in the distance to FLC gradient that the part has a red gradient in that little corner area. It is roughly 8% away from failing or distance to the flow limit curve. That gradient stays constant throughout the different gradients shown. For example, this is thickness reduction. The thickness reduction is showing that it is thinning roughly around 26%. So you can now see that it gives you a complete roadmap in different gradients to show you different information but in the same areas of where the concerned area is. It also maps it again to the forming limit diagram, which is showing you that the red points are really getting close to the flowing limit curve, which is showing a necking fault. The finite element model to the actual measurement. This is showing that the finite element model had predicted where the high stresses and strains were going to be on the part. The actual ARGUS measurement from the actual part showing you the exact same thing. This validates the FEM. This can help you go both ways. Fast forming analysis of parts. This is a breakdown of exactly how the ARGUS works. It's based on multiple images from different locations. It's automatic and complete computations, and based on ARGUS markers as we discussed before, by using coded targets and scale bars to give it a size ratio. The standard results are 3D coordinates and displacements, surface strain tensors like major, minor, and thickness reduction strains, automatic FLD reporting, transformations by best fit to CAD, distance from CAD surface to FEA geometry, and deviation from FEA results. Once the part is formed, it is undefined after opening the tool. The way you can change this is that you can align the measurement and the simulation by importing the FEA geometry, the measured tool geometry, or the CAD data, and best fitting the measurement data to the final imported FEA geometry. The result of this gives you a deviation calculation and strain geometry, meaning you can overlay the CAD data to the actual measured data from the ARGUS system directly in our system, and it'll give you a comparison color map and gradient to show you where the part is differing from the actual CAD data. Thank you for your attention. My name is John Psilopoulos, and this has been part 2. Please continue to part 3 for further information.